Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 11, Astigmatic Lenses. Now, we learned in Unit 10 about myopia or nearsightedness, that we compensate with minus sphere lenses, and we learned about hyperopia or farsightedness, which we compensate for with plus sphere lenses. Now, you can also have something called astigmatism, which is compensated for with astigmatic or cylinder lenses. Many years ago, there was an ad in the Yellow Pages. For those of you who are too young to know what the Yellow Pages were, they were a phone book of business listings, and the pages were actually yellow to distinguish that phone book from the white pages, which had residential listings. So in the Yellow Pages, businesses would often purchase ads to place near their listing. Sometimes they were 1 inch by 1 inch, and sometimes they actually took a full page, depending how much the business wanted to pay for their ad. And there was a misprint for an optical establishment that said that they offered astigmatic lenses. So these may have been lenses that had difficulty inhaling and exhaling, but I'm pretty sure it was a misprint. So we have on the left a cylinder lens where the axis goes along the flat meridian of the lens. You can think of it as the same as the axle of a wheel, right? And then 90 degrees away in that meridian, that has the steepest curve, and therefore that is the meridian of maximum power. Now, we don't say 0 for 0 power along the axis meridian. We say plano, P-L-A-N-O, abbreviated P-L. Now, let's say you wanted to figure out what the power was at angle theta from the axis. It's going to be something between 0, or plano, and the maximum power, and the formula is the power at angle theta with the axis is the power of the cylinder times sine squared theta. On the right, we have a cylinder, and as light hits that cylinder, it creates a line focus, not a point focus like a sphere, but a line focus. And we can see part of the line here and extends all the way to the end of the cylinder. So here is a cylinder. If this were made of clear plastic or clear glass, it would be an optical device that can focus light. But unlike the spherical lenses that we've talked about up to now, this does not focus light onto a point. So you can think of this cylinder as being a plus cylinder, plus because it has a convex surface. And remember from Unit 1 that light vibrates in all sorts of different directions. So the light that hits this cylinder in this direction is hitting a flat surface, and it will not be focused as it would if it were hitting a curved surface. Now, 90 degrees away from that flat surface is the maximum power of this cylinder. And that's an important concept to remember. The axis of a cylinder has no power. 90 degrees away is the maximum power. And so light that hits this cylinder in that direction will be focused into a point here behind it, 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 so it'll create a line. So the cylinder, the plus cylinder, creates a line focus that's parallel to the axis of the cylinder. We call a meridian This is the meridian that I'm talking about. We call a meridian that has no power, we say that the power isn't zero, we say it's plano, P-L-A-N-O, abbreviated P-L. So this is a representation of a plus cylinder lens. It has a convex surface. This is what you would find on the front surface of a meniscus lens. And this is a representation of a minus cylinder lens, a concave surface you would find on the back of a meniscus lens. Now, you can also have two cylinders put together, and that's called a cross-cylinder lens. The axes of the cylinders are 90 degrees apart. And when you send light through two plus cylinders, the plus cylinder is on the front surface of a meniscus lens, a minus cylinder is on the back surface of a meniscus lens. So here we have two plus cylinders, and you get first a line focus corresponding to the axis of the more powerful cylinder, the one with the steeper curve. Then you get the oval, then you get a circle, which is called the circle of least confusion. In optometry school, there was a corner in my classroom where a group of students who always had question marks above their heads sat, and they created a sign to put up in the corner called corner of most confusion. And then you get an oval, and then you get a line focus corresponding to the axis of the weaker plus cylinder. That interval from one line to the other line, that's called the interval of Sturm. There's a German expression, Sturm und Drang, which means turmoil and drama and anxiety in your life. So basically, the result of a country music song, you know, your spouse has left you, the kids disrespect you, the boss makes fun of you, even the dog hates you, you have Sturm und Drang in your life. So this is the Sturm without the Drang. You can also have what's called a spherocylinder, where a sphere is combined with a cylinder lens. So to determine the total power of a lens, you add the powers of the front and back surfaces of the lens in both meridians, the axis meridian and the meridian 90 degrees away. So here's an example. You want to find the total power of a spherocylinder whose front surface is a +2 sphere, and the back surface is plano -2 axis 180. That means that the axis meridian is plano, and 90 degrees away, it's -2. And the axis is 180 degrees. That means the -2 power is 90 degrees away from 180, or 90 degrees. So let's draw it out. We'll draw what's called an optical cross for the front surface, and an optical cross for the back surface of the lens. And we'll fill in what the powers are in the 90th meridian and in the 180th meridian. So this is the front. This is the back surface. So the front surface is a +2 sphere. That means it's +2 all over. It's +2 in the 90th meridian, and it's +2 in the 180th meridian. The back surface is plano -2 axis 180. So that means that in the 180th meridian, there's no power. That's the axis. And 90 degrees away, in the 90th meridian, there it's -2. Now we add up the powers in the 90th meridian, and we add up the powers in the 180th meridian to get the total power of the lens. So we see in the 90th meridian, it's +2 -2, that adds up to 0, or plano. And the 180th meridian, it's +2 + 0, or plano, that's +2. So the power of this lens is plano +2 axis 90. The power is 90 degrees away from the axis. When you look at eyeglasses, the right eyeglass lens is on your left and the left eyeglass lens is on your right. The way we arrange the degrees for cylinder purposes is they increase counterclockwise. The right side is 0 degrees, but we don't say 0, we say 180. And then they go up through 45 degrees up to 90 degrees on the vertical meridian. And then it continues going counterclockwise to 135 degrees and then 180 degrees on the left side. Now, eyeglass prescriptions can be written both in plus cylinder form, where the cylinder is on the front surface, or minus cylinder form, where the cylinder is on the back surface. Eyeglasses are generally manufactured in minus cylinder form. Some eye doctors like to write their prescriptions in plus cylinder form. So it's important to know how to transpose prescriptions, either going from plus cylinder to minus cylinder or going from minus cylinder to plus cylinder. So one way to do it is to algebraically add the sphere and the cylinder, to change the cylinder sign, and then to add 90 degrees to the axis. The other way to solve the problem is to draw an optical cross and to fill in the powers in the major meridians. So here's an example. We want to change +5 sphere, -2 cylinder, axis 90 to a plus cylinder prescription. So a +5 sphere means that it's +5 all over, both in the 90th meridian and the 180th meridian. -2 axis 90 means there's -2 in the 180th meridian, 90 degrees away from 90. Then we add up the powers in the 180th meridian to get +3, and we find our new power is +3 +2 axis 180 to achieve +5 in the 90th meridian. So I have here a cross cylinder +6 axis 90 +450 axis 180 that I'm slowly moving away from and toward a wall and back again to show you the interval of Sturm. The lines are not quite clear because I'm using a diffuse light source, but it gives you a good idea of what the interval of Sturm looks like, going from one line to an oval to the circle of least confusion to an oval to the other line.